We are taking the theoretical problem solving, all those pseudocode exercises and flowcharts from the last phase of this series and turning them into a living, breathing C++ program.
Which is explaining C++ basics for complete beginners.
Exactly. We're looking at a basic hello world and an interactive average calculator. Step 1, the programmer writes the source code. Step 2, compiling. And step 3, executing.
Right.
I mean, I understand that source code is what I type on the screen, but why do we need this middleman? Like, why can't the computer simply read the C++ logic directly?
Well, the physical hardware of a computer doesn't process logic or English or even mathematics in the way we understand it.
Wait, really? It doesn't understand math?
Not our kind of math, no. At its lowest physical level, a computer's central processing unit, the CPU, is just a vast architecture of microscopic switches.
Oh, I see. Like physical light switches.
Pretty much. It only understands two states, on and off, high voltage and low voltage.
Right.
And we represent those states conceptually as, ones and zeros. That is machine language.
Just massive walls of ones and zeros.
Exactly. But source code, on the other hand, is designed for human readability. It relies on alphanumeric characters, standard mathematical symbols, structural formatting.
So the source code is a compromise. It's a language that humans can read and write efficiently, but it is fundamentally alien to the CPU.
Precisely. The gap between your typed intent and the electrical signals required to execute that intent is impossibly wide.
So that's where the compiler comes in.
Yeah, this is why the compiler is absolutely necessary and why the text specifically notes that C++ is a compiled programming language.
Got it.
The compiler is it's an extraordinarily sophisticated piece of software whose sole job is to ingest your human-readable source code, analyze the logic, and just map it down to the exact hardware-specific machine instructions required to execute it.
That is wild. We have this highly rigid translation process, this completely unforgiving compiler demanding perfection. Yet, ironically, the very first line of our Hello World code block in the source is this: / my first C++ program.
Yeah, the comment.
Right. And the text explicitly states that this is a comment, and the compiler completely ignores it.
Completely ignores it, yes.
Why are we writing plain text in a machine environment if the machine is specifically told to ignore it? I mean, isn't that a waste of time?
You'd think so, but no, because code isn't just written for the machine.
Really? Who else is it for?
It's for other humans. The compiler is the translator for the computer, but the source code itself is also the primary means of communication between developers.
Oh.
The text notes that comments help programmers describe what the code is doing, or, they leave notes for themselves.
Two ways to implement this context. The first is the single line comment, which begins with 2 forward slashes.
Right.
The rule here is that everything after those slashes on that specific line is treated as a comment.
The moment the compiler parses those 2 forward slashes, it just purges the rest of that specific line from its memory buffer and moves to the next line of code.
It just drops it completely.
Completely. It doesn't attempt to translate it. It doesn't validate its grammar or try to understand it at all.
And if we need more space, the text provides the block comment. It begins with a forward slash and an asterisk, and ends with an asterisk and a forward slash.
Yeah, that's for broader documentation. You open the block comment and the compiler essentially puts on blinders.
Okay.
You can write paragraphs of text, span multiple lines, format it however you want, and the compiler will completely ignore all of it until it detects that closing delimiter.
That's actually really cool. It's like a protected space for human thought inside this rigidly mechanical document.
Exactly.
All right, let's move past the ignored text and look at the first instruction the compiler actually processes. Line 1, hashtag include, and then in angle brackets, IOStream.
Yep. And the first functional line we hit in Hello World is called a preprocessor directive. It says #include IOStream.
This is where we start gathering the tools necessary to build the application. IOStream stands for Input-Output Stream Library. Does this happen before the translation phase we just talked about?
Yes, it does. The preprocessor is a separate step that runs just before the compiler. When it sees that include directive, it literally goes into the system files, locates a massive file named IOStream, and copies all the pre-written code from that file directly into the top of your program.
Wait, it literally copies the code?
It physically copies it, yes.
So my tiny, 5-line program suddenly becomes thousands of lines long behind the scenes before it even compiles.
That is the exact mechanism. You are inheriting all the complex logic required to interface with the operating system's display drivers and keyboard inputs. logic that was painstakingly written by the architects of the C++ language.
But why make me ask for it? Like, if displaying text and taking input are so fundamental, why doesn't the compiler just automatically include the IOStream toolbox in every single program?
That's a good question.
It just seems like an unnecessary step to force me to write it out every time.
It really comes down to memory efficiency and compilation speed. You see, C++ is designed for high-performance computing.
Bro.
If every program automatically loaded every standard library like networking, 3D graphics, advanced mathematics, file system management, your tiny Hello World application would become incredibly bloated.
Oh, I see.
The compiler would waste time translating thousands of lines of unused tools. By forcing you to explicitly declare include IOStream, the language remains modular and lightweight. You only carry the tools you actually intend to use.
That makes a ton of sense. Hey, before you compile my logic, go find the standard toolbox that knows how to handle input and output and physically paste that code into my document.
That is precisely how the preprocessor operates.
Wow.
It resolves the directive by fetching the IOStream library and incorporating it, which grants your specific program the ability to communicate with the monitor and the keyboard.
Then without it.
Without it, the compiler would encounter an output command later on and throw a fatal error because it would have absolutely no reference for what you're asking it to do.
Okay, that makes total sense. Which brings us directly to line 2, using namespace STD.
This is a mechanism for scope resolution.
Scope resolution. Break that down for me.
Well, when you import a massive library like IOStream, you are bringing in hundreds of predefined tools. To prevent naming collisions, imagine if you wrote a custom function in your code called count, and the library also has a tool called count.
The compiler wouldn't know which one to use.
Exactly. So to fix that, the library encapsulates all of its tools inside a specific namespace.
Okay.
And the standard library uses the namespace STD.
So if I'm importing multiple libraries into a really large code base, namespaces ensure the compiler knows exactly which version of a tool I'm referencing.
Yes. By default, to use the standard output tool, you would actually have to write std.count.
Oh, explicitly stating the namespace and then the tool.
Right. And if you have a program with thousands of lines of output, writing that prefix repeatedly adds a lot of visual clutter and cognitive load.
So using namespace STD acts as a global announcement to the compiler.
Exactly.
We're essentially saying, for this entire file, if I ask for a tool and don't specify where it came from, just assume I want the version from the standard library.
Spot on. It's an efficiency hack for the developer. It keeps the code clean.
It streamlines the syntax so you can just type count.
Exactly.
Okay, so we have our documentation in place with the comments. We have imported our I/O capabilities with the include directive. We have defined our namespace.
We're setting the stage.
No, we finally reached the actual architecture where the execution occurs.
The main event.
The source text points us to this line, int main, followed by an opening curly brace, and eventually a closing curly brace.
Right. This is the mandatory entry point for execution.
Mandatory.
Yes. In C++, man, every single program, regardless of its complexity, must contain a main function.
I want to try and visualize how the operating system interacts with this.
Go for it.
When I double-click an executable file on my desktop, the operating system, whether it's Windows, Mac OS, Linux, whatever, acts as a loader, right?
Okay.
It allocates memory for the program, and then it has to hand over control to the code.
Yes.
So main is the specific memory address the OS is trained to look for. It's basically the front door.
The front door. I like that.
If the operating system scans the compiled binary and cannot locate that main entry point, it just abandons the execution.
Exactly. The OS requires a guaranteed standardized point of entry to instantiate the process. Main provides that contract.
Okay, now preceding the word main, we have the word int, which stands for integer.
That defines the return type of the function.
What does it mean to return a type?
Well, when the operating system hands control over to main, it expects a status report back when the function concludes.
Oh.
The int signifies that the status report will be a whole number, an integer.
Now, the source notes wisely suggest that beginners shouldn't get totally bogged down in this return value just yet, but understanding that contract between the OS and the program is definitely crucial.
Absolutely.
We will circle back to how that integer is actually delivered at the very end of the execution block.
Good idea.
But immediately following main, we have those curly braces. The source states, everything between these braces belongs to the main function.
So if main is the door, the curly braces define the structural boundaries of the room.
The walls.
Exactly. In computer science, we refer to this as defining the scope or the block of code.
So by enclosing the instructions in curly braces, you aren't just organizing it visually for yourself, right?
No, it's way more than visual organization.
You are creating a hard boundary in the computer's memory.
Yes.
You're telling the compiler, these instructions are explicitly contained within this specific function. When the function ends, this scope terminates.
The compiler relies entirely on those braces to understand the hierarchy of your logic.
Because it ignores white space, right?
Exactly. It ignores tabs, empty lines, everything. The braces dictate the beginning and end of memory lifetimes for that specific block. Okay, so the final piece of architectural plumbing in our main block, right before the close-in curly brace, is the statement, return 0.
This is how we exit the program gracefully. Okay, so we are officially inside the main block. We're in the room.
We made it inside.
We have our IOStream library ready. We're finally at the point where we instruct the machine to act.
Let's see the code.
The line is count, followed by 2 less than signs, followed by, quote, hello world, unquote.
Let's unpack the components of the statement. First, we have count, which the source defines as character output.
Right, this is the tool we borrowed from the IOStream library.
Exactly. And then we have the 2 less than signs, which the text calls the insertion operator. They send information to the output stream.
Anything inside quotation marks is displayed exactly as written.
Because the quotation marks define what is called the string literal. This is a critical signal to the compiler.
What is the signal?
It tells the translation engine, do not attempt to parse the text between these quotes for C++ commands, variables, or logic. Treat it purely as raw visual character data and pass it directly to the output stream.
So it bypasses the logical evaluation entirely. If I spell it as hello world with a U, the compiler doesn't throw an error or try to fix it.
Not at all. It just faithfully displays the typo.
Because inside those quotes, the strict rules of C++ syntax are suspended. It is purely data meant for human consumption on the monitor.
Precisely.
If you forgot those quotation marks, the compiler would look at the word hello and try to find a variable or a function named hello.
It would treat it as a programmatic command.
Yes, and it would fail to find it and throw an error. The quotation marks isolate raw human text from executable machine logic. Then we reach the end of the instruction, which introduces one of the most infamous elements of C++ syntax.
Oh boy, here we go.
The semicolon. In C++, almost every statement ends with a semicolon. The semicolon tells the compiler, this instruction is finished.
It's the ultimate hard stop. The semicolon is not punctuation.
Okay.
It is a structural terminator. It flushes the parser's current state and resets it for the next instruction.
Finally, just before the closing brace of our main room, the text highlights the phrase return 0, followed by a semicolon. It says this tells the operating system that the program finished successfully. Congratulations, you've written your first C++ program. Printing static text is only the beginning. Printing text is useful, but programming becomes much more interesting when users can enter their own data. To build a slightly more complex program based on the pseudocode from a previous lesson. The objective here is to engineer a program that requests 2 distinct numbers from the user, calculates their mathematical average, and outputs the result.
A very practical application. And the setup remains identical. We still include IOStream, we still use the SPD namespace, and we still enter through int main.
The structural walls are the same.
Exactly. But the internal logic is fundamentally different now.
The very first line inside the new main scope introduces a fundamental concept of memory allocation.
Yes.
It reads, float num1, num2, average.
We are declaring variables. A variable is, at its core, a named reservation in the computer's random access memory, or RAM. Instead of forcing the programmer to memorize raw hexadecimal memory addresses, the compiler allows us to assign human-readable labels to those memory blocks.
So num1, num2, and average are our labels.
Yes.
But preceding those labels is the keyword float.
Right.
The source identifies this as a data type.
It is.
Why must we explicitly declare the data type? If we're just storing data, why does a compiler care what format the data takes before we even store anything?
Because memory allocation is a physical process.
Physical process.
The compiler needs to know exactly how many bytes of RAM to reserve for each box, and it needs to know how to encode the binary data that will eventually be placed inside.
Okay.
An integer, a whole number, is relatively straightforward to encode in binary. But a floating point number, a number with a decimal like 3.14, is incredibly complex.
Because it has to store the digits, the position of the decimal point, and potentially handle massive scale differences, right?
Exactly. So we are pre-formatting our memory reservations.
Yes.
We have our 3 empty float blocks ready in RAM. Now, we need to populate them with data generated by the user.
We need input.
The code executes a prompt. Count, enter first number.
Which we know pushes the text to the monitor.
Right. But the subsequent line is where the interaction happens. It says, syn num1.
Okay, so if count is character output, syn is character input.
Okay.
This screen monitors the standard input device, which is the keyboard.
I am looking at the operators here. With count, the insertion arrows pointed left, pushing data out to the screen.
Right.
With syn, the extraction arrows that are pointing to the right, away from the input stream, and directly toward our memory label, num1.
The syntax visually represents the flow of data across the system bus.
When the execution reaches syn, the program effectively halts, doesn't it?
It does. It's a blocking operation. It waits indefinitely for the user to type a value and press the enter key.
Yes. The OS puts the process into a wait state.
Okay.
Once the enter key sends the interrupt signal, syn captures the keystrokes from the input buffer.
And then?
The extraction operator takes that data, converts it into the float binary format we prepared earlier, and physically writes it into the memory address associated with the label num1.
Okay, so if the user types the number 20, the question mark in our visual diagram's first box disappears, replaced by a 20.
Exactly.
The program then repeats this interactive loop for the second number, prompting with count, pausing for syn, and writing the input into the num2 memory block.
Let's assume the user inputs 30 this time.
Okay, 30. We now have 20 stored in num1, 30 stored in num2, and our average block remains totally empty in RAM.
The memory's populated. Now the CPU must process it.
The code progresses to the calculation phase.
The math.
The line is average num1 plus num2.
Right.
To anyone with a background in basic algebra, this looks like a standard mathematical equation.
It does look like one.
In C++-IN, a single equal sign is not evaluating whether two sides balance.
This is a massive paradigm shift for beginners.
Tell me more.
In mathematics, an equal sign is a statement of truth or equivalence.
Like 2 plus 2 equals 4.
Right. But in system architecture, the single equal sign is an active command. It is the assignment operator.
It's not a question. It is a directive.
Yes.
How does the compiler sequence this directive at the hardware level?
It forces a strict right-to-left execution path.
Right to left.
The CPU completely ignores the left side of the operator initially. Its absolute priority is to evaluate the expression on the right side, boil it down to a single value in its registers, and only then look to the left side to determine where in RAM to store that final value.
Let's trace the exact hardware sequence for our specific inputs, the 20 and the 30.
Let's do it.
The CPU targets the right side, num1 plus num2.
First, respecting standard order of operations, it evaluates the parentheses.
Okay.
The CPU sends a fetch request to RAM for the addresses labeled num1 and num2. It pulls the binary values 20 and 30 into the processor's arithmetic logic unit, or ALU.
The ALU adds them together, holding a temporary value of 50 in a register.
Next, it processes the division operation, represented by the /.
Right.
It divides the 50 by 2, resulting in a final evaluated value of 25. The entire right side of the expression has now collapsed into a single piece of data.
And it is at this exact microsecond that the CPU finally acknowledges the left side of the assignment operator.
Yes.
It sees the label average. It takes that 25 from its temporary register, travels across the bus to the RAM address we reserved for average, and overwrites the empty space with the new binary data.
The assignment is complete.
Wow.
Understanding that physical movement of data fetching, computing, assigning, and storing is what separates someone who just copies tutorial code from someone who actually engineers software.
It's so mechanical when you break it down like that.
It really is.
So we have collected the data, processed it through the ALU, and stored the result. The final step is to retrieve that result from memory and display it so the user can see it.
We need output again.
The final output line is count average. Average. Notice anything different.
This line is unique because it utilizes the extraction operator twice in a single command.
It is chaining the stream.
Chaining.
You can queue multiple discrete pieces of data onto the conveyor belt in a single instruction.
Okay, let's break down the queue here. The first item on the belt is average. Average.
Yay.
Because it is wrapped in quotation marks, the compiler treats it as a string literal. It will push those exact characters to the screen without any analysis.
Correct.
But the second item on the belt is the word average, and crucially, it is not in quotation marks.
That absence of quotes triggers the compiler's memory retrieval protocols.
Okay, how does that work?
When it sees an alphanumeric sequence without quotes, it assumes it must be a variable identifier.
Oh, I see. It queries the symbol table, locates the memory address for average, fetches the stored value, which is 25, and drops that numeric data into the output stream.
So on the monitor, the user sees the static literal text instantly followed by the dynamic memory value, average 25.
Yep.
The transition is totally seamless. The user experiences a cohesive response, but mechanically, the CPU just sequentially flushed two entirely different data types out of the buffer.
It creates the illusion of intelligence.
It really does.
But as we've established, the machine has absolutely no intelligence. It is just executing your meticulously structured architecture with blistering speed.
What has actually been accomplished?
Well, you've learned that C++ is a compiled language, meaning a rigid translator must convert your human-readable source code into machine language before execution.
You've learned that you can leave context and documentation for yourself and others using comments, which the compiler gracefully ignores.
You know that before you can interact with the system, you must import the necessary toolboxes using preprocessor directives like include IOStream.
You understand that the operating system requires a specific entry point, which is why every program must have a main function, and that curly braces define the architectural walls of that function's scope.
You've seen the absolute strictness of the compiler, realizing that forgetting a simple semicolon will crash the translation process because it acts as the non-negotiable full stop of an instruction.
You've mastered sending data out with count and capturing data in with syn.
You understand that declaring variables like floatnum1 is actually a command to reserve specific chunks of RAM for specific types of data?
And perhaps most crucially, you've learned to unlearn high school math, recognizing that the equal sign is an assignment operator that calculates the right side first and actively stores the result in the left.
That is an immense amount of foundational architecture. Thank you for joining us on this deep dive into the foundational architecture of C++. If you've tracked the journey of data through these two programs today, you have conquered the hardest part of the learning curve, the conceptual shift.
You are now equipped to dive into the deeper intricacies of complex data types, sophisticated loops, and advanced operators. Keep building. We will see you next time on the Deep Dive.